we get into the actual content, I did want to flag a couple of resources that I relied heavily on while pulling together this course, and also that you all should definitely reference if you are planning to do text analysis in the future. And so the first one is a textbook that's available online called Text Mining with R, which is very beneficial. And then also Chris Bale's publicly available Text is Data course. I pulled a lot of code from that course for this workshop today. And it also has some more details and extensions that will definitely be valuable if you are planning to conduct your own text analysis. Okay, so what is text analysis? So text analysis, also called text mining or natural language processing, is the process of extracting meaningful information from text data. It involves examining words, phrases, and patterns to really uncover insights, trends, or hidden relationships within text. And so this combines techniques from linguistics, statistics, and machine learning to interpret and manipulate human language. So text can really come in a variety of forms. This ranges from recipes and song lyrics to books and news articles to tweets and performance reviews or journal reviews. We can get a hold of a lot of useful information from this text, including extracting key themes and sentiments, which we will review today. I included this meme here because it is personally one of my all-time favorites. I still don't know what accounting is. And I think it really speaks to something about text analysis that at some haters, for example, might say that it is really just counting words. And even though counting words does play a very valuable role in text analysis is more than that. And I hope that that will be one of the key takeaways that we can take from this workshop today. Okay, so before we jump into content, I do want to introduce a few key terms that I'll be using today. These are terms that refer to the different levels of analysis in the text analysis process. So at the highest level, we have the corpus, which is the body of text that you are studying. In the example that we will be using in R today, the corpus will be the lyrics of all Taylor Swift songs. Alternatively, corpus could be the text of thousands of articles that you are examining. Within a corpus, there are several documents. In this Taylor Swift example, the documents are songs. However, we could also redefine the documents to instead be albums. Again, if our corpus is a collection of articles, the document would be the individual articles within the collection. And then lastly, within each document, we divide the text into tokens through a process of tokenization. And these tokens are the basic building blocks for your analysis. So often they're single words, but they can also be sentences, sequences of words called n-grams, where n is adjusted for the number of words included in the sequence. All right, so I guess at the highest level, text analysis really involves two initial questions. So first, how are you going to represent your text? And then second, what are you going to do with that representation? And so we'll be going through each of these questions today. So first, how are you going to represent your text? So before you even decide how you're going to represent your text, you do have to choose a coding language and package to use for your analysis. So within your coding language of choice, there are many different tool sets that are used for text mining and analysis. For this workshop, we're going to be using the tidytext package in R. And so, as I mentioned before, text data can really come in a variety of forms. So depending on your research question, you will have to define your corpus, documents, and your tokens. And then once those levels are defined, you can start to think about how you actually want to represent your text. The most common approach is to represent documents as individual words and their frequencies. This is called the bag of words approach because it does not take into account word order or any outside context. Instead, each document is treated like a bag of words. However, instead of counting individual words, you could also count phrases of multiple words. And so this is shown in the diagram on the right side here. So for example, the 2-gram consists of counting all 2-word sequences in the document. So in the sentence, this is a sentence, we see 3 different 2-grams. We see this is an A sentence, and the frequency of those 2-grams would be counted within the document. So this is kind of a longer explanation of the bag of words approach. I did want to just take a second to talk through this because this is the representation underlying the approaches that we will be going through today. So at the top, we start with a corpus, which in this case consists of 3 different sentences. And then the corpus is converted into tokens in the second step here. So we see tokens identified for each unique word within the corpus. And then from there, we create a vocabulary of unique words. And then the frequency of each word within each document is counted. And then in our final step, we see the vectors on the bottom right side here, which are the representations of the documents in this bag of words approach. So again, the first document in this example is the sentence, "The dog is happy." So we see D1 coded as dog having 1 occurrence, happy having 1 occurrence, is having 1 occurrence, and the having 1 occurrence, and that is then represented in a vector form. All right. So at baseline, the bag of words approach counts the number of times a word appears in a document. When we divide that number by the total number of terms in the document, we get the term frequency. And so again, this is measured at the document level. You can see the equation for that here. And so while term counts and frequencies seem fairly simple, they can also provide super interesting insights. One place we see this is in the Google Books Ngram viewer. I'm not going to take time to play around with this today, but I definitely went down a rabbit hole while prepping this and was playing around with the different frequencies of words that appear in Google Books across time. So highly recommend if you are looking for a rabbit hole for today. We really can take a lot away from just looking at word frequencies. Okay. The problem with word frequencies is that there are some terms that just appear frequently throughout a text. So for example, words like the and, which are stop words, are likely to appear frequently in text. However, there might also be other commonly used words that appear within a corpus. So not to give too much away from the analysis that we'll be doing, but one of those words for Taylor Swift lyrics is love. She talks about love a lot. So looking at the presence of the word love doesn't really allow us to distinguish among the different songs in her discography. And so instead, what we can do is we can calculate the inverse document frequency to see which words characterize the different documents within the corpus. And so what this measure does is it decreases the weight for commonly used words and increases the weight for words that appear several times within a single document, but not as much across different documents. And so we see this in the equation below. So basically, what happens here is the fewer documents that contain the term, the higher this fraction will be, and then the higher this whole term will be. And so that then increases the weight if the term does not appear very frequently across multiple documents. And so what this does is also, can you guys like see my Zoom video thing on the recording? Like you don't see like your own faces, right?
No.
Okay, good. Awesome. I just wanted to make sure because I can see that on my end and it's like blocking part of the screen. So anyway, okay. Awesome. Glad to hear that. So basically the IDF is technically a rule of thumb quantity. Its theoretical foundations aren't super firm, but it does allow us to identify words that are important in different documents within the text. And so basically it focuses on terms that, again, are less frequent, but more relevant within specific contexts. And it's using things like search engines to prioritize documents with keywords that are relevant to the search. And so what this allows us to do is we can actually multiply term frequency by the inverse document frequency to get the TF-IDF. And this value can be informative on its own, or it can also be used to weight the bag of words vectorizations of documents. So on its own, as I mentioned, it can be used to help search engines identify the most relevant documents in response to a search. It can help with content tagging and topic modeling by identifying keywords. It can also help in things like spam detection and document categorization. As I mentioned, it can also contribute more information to the vectorization of the documents within your corpus. And so, as I mentioned, the bag of words approach is a very simple vectorization where each document is represented as a vector of word counts. But then if we were to use the TF-IDF in this representation, what we would do is we would actually weight each word by its uniqueness across the entire corpus. So words that appear frequently in one document but are rare across the corpus would receive higher scores and therefore have more weight in that vectorization. Okay. And so I did want to call out that there are other ways to represent documents, to vectorize documents. One of these methods is Word2Vec, which is actually a neural network-based technique for vectorization. We will not be talking about this today, but just know that it is more advanced than the bag of words approach and the TF-IDF approach because it allows for language to actually be understood contextually, so it can capture more semantic relationships like synonyms and antonyms, but it does not handle out-of-vocabulary words very well. Okay, and then I did provide this summary slide. It's helpful to just sum up the different types of vectorizations that you can use to represent your documents. But any questions on this before we take a look at this in R? All right. Let me see if I can navigate over. Okay, can you see my R? Awesome. So as I mentioned, very important analysis today that we will be doing is of Taylor Swift lyrics. So this is the data frame that we'll be working with. As you can see, we have Taylor Swift. Title represents the song titles. We have albums, years, dates. And then this column over here that is titled lyric contains all the lyrics to her songs. And so what we're going to do is we're going to convert this data frame into a tidy text format. As I mentioned, this is a package built for text mining in R, and it's compatible with other tidy tools. So what we're going to do is you would, of course, install the packages if you didn't have them already, but here I'm just going to load them from my library. And first, what I'm going to do is convert my initial lyric data frame into the tidy text format with words as tokens. So what we'll see here is that I have selected the songs as our documents. So we have the title here for document and the word over here, which is at our token level. So for those of you who are familiar with the song Cardigan by Taylor Swift, you can just read down here. These are the lyrics to her song. But again, you can see that each row represents a unique token for that song. We can also change the token argument to have different units. So as I mentioned, I first selected the tokens to be individual words. We could also have our tokens be different n-grams. So what I wanted to do as an example is just show you what it would look like if the token of our analysis was instead a 4-gram. I'm going to run this code. And so now instead of only having one word in our token column, we see sequences of 4 words in the token column. But for the purposes of this analysis, we are going to use single words as our tokens. So what we're going to do next is look at the frequency of words within the corpus of Taylor Swift lyrics. So when we take a look at these word frequencies, we can see that we frankly have a lot of stop words. We see you, the, and, to, a. All of these words don't really give us information about the content of her songs. So thankfully, Tidy Text has a data set built into the package that includes a bunch of stop words from 3 different lexicons. And what we can do is remove all the stop words from our data set. So now, if we look at word frequency, we see a bit of a different story. We see that the word love is actually the most popular with 738 occurrences throughout the entire corpus. And then we see, a few other kind of strange things like the number 05. This data set is not perfect, and I think includes things like transcriptions from speeches as well. So I think we're just getting some different noise here. So thankfully, again, Tidy Text has a bunch of different tools that we can use in order to clean up our data. I included some other types of pre-processing steps that you might want to consider in the comments here. So for example, converting to lowercase, which is actually automatically done in the initial tidy text function. But also you can remove white space, remove punctuation, remove numbers. You can do what's called stemming, which is converting a word to its most basic conjugate form. So for example, swim and swimming would both be converted to swim. However, stemming does only chop off the last letters of a word, so it might result in kind of some strange matches. Instead, you can do what's called lemmatization, which actually uses a dictionary to identify the meaning of the word and replace it with the more basic form of the word. I included a link if you want to read more about it. We're not going to go into details about that today, but the one thing about this data set is we do see some weird numeric occurrences. So I'm going to run this code here in order to remove numbers. And so now this time, if we look at word frequency, that weird 0.5 that was occurring is no longer in our data set. So I'm feeling pretty good about the data cleaning here. And so now what we can do is we can actually just do some basic word frequency analysis. So first, I'm just selecting the top 20 words from my data set. And then what I'm going to do is actually plot them. And so we can see the number of times words appear in Taylor Swift songs in our chart over here. Again, we see that love is our most frequent, and we could theoretically do analysis on the frequency of these other words that appear. And then the last thing we'll do here is actually calculate the term frequency inverse document frequency to identify unusual words that might differentiate among the different songs that we have. So I'm actually running this code. And so if we take a look here, this is a data frame sorted by the TF IDF of the different words. So we see the word A disproportionately appears in the song Wonderland. So again, what this means is that it appears mostly in this one song. So we see that the IDF is very high. And when we multiply by the TF, we get the TF IDF that is also high, which is why this is flagged. We see woods most frequently appears in out of the woods. And so these are the types of words that might be important if we were trying to characterize the different Taylor Swift songs, or again, like do a search within the songs for particular topics. Okay, any questions on that initial frequency?
I have a question, Jenna.
Yes.
And I honestly don't even know enough to know if this is a valid question, but with the n-gram, so say if you did the 4-gram, so
Mm-hmm.
that's counting the frequency of when those four words in particular occur together in that exact order.
I believe so.
Okay.
Scott, correct me if I'm wrong on that.
Can you repeat the question?
So for a 4-gram, for example, looking at the four words that occur together, um, is the frequency only counted if those four words occur in the same order, or do they just have to exist together in some way?
It usually has to be the same order because with the n-grams, if you're changing the order, it actually ends up being more or less the same as a word in a bag approach.
Okay,
Not
right.
explicitly, but yeah, usually it has to be in the same order.
Okay. And so then second question to that, for a 4-gram, for example, that is where the words are spliced together is chosen automatically based on the starting word of the document. Like you can't go in and okay, thank you.
Actually, I did want to, let's go back to the code and just take a look at what the 4-gram looks like, because one of the things that you'll notice, I actually have it here, is, I mean, the first lines of the song are vintage tea, brand new phone, high heels on, right? So we see that in the first token, vintage is the first word, but then the next token starts with the word tea. So it's only moving by one word at a time. Yeah. So you're not actually getting the first four words and then, the next four words, you're moving one by one through the text. Okay, cool. Let's go back to the slides. So as I mentioned, that is kind of the initial stages of just word frequency and how we're actually going to represent our text. But now we have to figure out what we're going to do with that representation. So there are a few different things we can do with our text data. Today, we're going to be focusing on kind of some basic sentiment analysis and topic modeling. And then at the end, we'll briefly touch on some other use cases, which hopefully Scott can provide some more insight on than I can, because as I said, I'm more focused on the basics for now. All right, so first to start with sentiment analysis. So at kind of the highest, simplest level, dictionary-based sentiment analysis is a type of rule-based classification. So basically what happens is in this analysis, we're considering the sentiment of each word within a document and then aggregating the sentiments within a document or within a corpus to kind of get a sense of the overall sentiment that is appearing. There are other sentiment algorithms that look at units of analysis that are higher than just words, such as sentences, and can account for more complicated grammatical structures like negation, but we're going to focus on kind of the more basic dictionary-based approaches here, but those are some examples of other packages if you are interested in looking into that. All right. So thankfully, Tidytext has various sentiment analysis dictionaries available within the package. So there are 3 main lexicons available for sentiment analysis. And so the lexicons are dictionaries where a bunch of different words are assigned to different sentiments. And the scoring of the dictionary of the lexicon just varies by the lexicon. If you do have your own specific vocabulary or word meanings that are particularly important to your analysis, you can also build your own lexicon and then apply sentiment analysis in this way. So essentially, as I mentioned, dictionary-based sentiment analysis just has this dictionary of words with sentiments, and then it matches the words to your corpus, to the lexicon, to the tokens of your data, and then you can aggregate your data as needed for analysis. So in the Taylor Swift example, what we'll see is we can aggregate it to the song level, but we could also aggregate it to the album level or to the date level if we wanted to. So this is a table summarizing each of the lexicons within the Tidytext package. So first we have the AFIN lexicon, which scores words from -5 to 5, with negative scores indicating a negative sentiment, positive scores indicating a positive sentiment. Then we have our Bing lexicon, which is just a binary positive or negative for each word. This is the simplest lexicon, but it's also the most widely used. It incorporates a large number of words, and it's also very well studied. And then lastly, we have the NRC lexicon, which is also binary, but instead it flags if a word fits into various categories. So it flags if a word is positive or negative, fits into categories of anger, anticipation, disgust, fear, joy, sadness, surprise, trust. And so a word can be flagged as in many of these categories as well. So then on the next slide here, this is just the sentiment analysis workflow in Tidytext. We're not going to spend too much time here because we're actually going to go implement it on the Taylor Swift data. But this is here for your reference if helpful. So let's actually go back to R and go back to our sentiment analysis. So first, what we're going to do is we're going to load in the 3 different lexicons from the Tidytext package. Sorry, you actually do have to install the package text data. That's just commented out. So if you need to use it, feel free to uncomment it. But let's actually take a look at how each lexicon differently categorizes the word love. So first, what we'll do is we'll take a look at the AFIN sentiment. So the AFIN sentiment, the AFIN lexicon, as a reminder, scores words from -5 to +5 with positive values indicating more positive sentiment. So it gives love a score of 3. The Bing sentiment, the Bing lexicon is binary and it flags words as either being positive or negative. So here love is flagged as positive. And then NRC flags whether different words fit into different categories. So here we see that love is flagged as fitting in to the sentiment of joy and the positive sentiment. So what we can do, as I mentioned, is we can aggregate sentiment across different units. So what I want to do first is actually look at how the average song sentiment for Taylor Swift has changed over time. So in this code here, I'm calculating the mean sentiment per song title per date. And now what I'm going to do is graph the mean sentiment over time. And so this is using the AFIN lexicon. So we're scoring sentiment again from 5 to -5. You don't really see a trend in the sentiment over time. Yeah, I don't really think we can characterize that. So rather than look at songs by date, what I want to do is actually look at mean sentiment per album. So once again, we're going to use the AFIN lexicon. And as I mentioned, the data set is a little bit messy. So I'm actually going to filter for her core albums into this different data set. And then we're going to graph the AFIN sentiment by album. And so here we can see the Taylor Swift album, which is her debut, has an overall sentiment score of 1. And so, sorry, let me take a step back. What I did here is I took the average sentiment per song per album. So this is all at the song level, I believe. It might actually not be. I'm not going to spend time looking at the code now, but overall what we can see is that the Taylor Swift album has the highest sentiment. We see that she was in kind of a sad girl era with Evermore and Folklore, which for those of you who are familiar with Taylor's discography, that does fit. We can also look at a different question of how mentions of joy have changed over time. So here what I'm doing is I am merging our Taylor Swift tidy text lyrics with the NRC sentiment, and then I'm filtering for any mentions of the joy sentiment. And I'm going to plot mentions of joy over time. So here we see, again, not really a consistent trend in mentions of joy over time, but I just wanted to give a sense of the different types of analyses that we can do with some of these more basic dictionary-based sentiment analyses. Any questions on that? Okay. Great. Okay, so I did want to talk for a minute about some of the advantages and disadvantages of sentiment analysis. I don't know, have people used sentiment analysis before? Sort of, you encountered disadvantages or advantages that come to mind?
Wait, sorry, were you asking us for advantages?
Yeah, I mean, if you have any, then please participate. If not, I can also just keep talking.
I guess a disadvantage is that it's hard to take into account context. So, somebody could mention love, but they could mention it in a negative sense or like sarcastically, and how can you can't really capture that with normal sentiment analysis.
Yeah, that's a great point. Definitely is one of the key limitations of this approach. All right, I'll just keep talking. So some of the advantages of dictionary-based sentiment analysis is that it's really simple logic, pretty easy to implement. It's also scalable to large data sets. And even though it's a noisy measurement, it does tend to agree with human raters. Also, credit to Scott for the information from the slide from his undergrad course. And then some disadvantages of dictionary-based sentiment analysis is that it does assume that words have one meaning, and it's hard to deal with more complex themes. As Jacob mentioned, it doesn't really account for modifiers and sarcasm, and it can't really account for sentiments that are communicated through multiple words at a time. All right, so next we are going to talk about some kind of basic topic modeling. So at the very highest level, topic modeling is a method that is used to classify documents within the corpus. And so essentially what it does is it analyzes bags of words together, and as an output, each document is assigned a probability of belonging to a particular topic. And this method is technically unsupervised machine learning because topics are identified by the model. They're not pre-specified by the researcher. This was a nice graphic here, kind of explaining how it works, but rather than explain the graphic, I'm going to go through the steps that I have written out on the next slide. So the kind of most basic, most common form of topic modeling is LDA. I'm not going to try to pronounce those words. I'm just going to refer to it as LDA. And so in this type of topic modeling, the researcher first specifies the number of topics within the corpus, and then words are assigned to one of the topics according to a statistical distribution. And then topics are updated iteratively based on the prevalence of the word across topics and the prevalence of topics within the document. And assignments stop updating past a researcher specified threshold or when iterations stop affecting probabilities. And so then the output here is the list of words associated with each topic. And then you also get a probability that each document is associated with each topic. And so I did want to call out here that in this LDA approach, the input document is represented as a bag of words vector. So this means that it does not account for ordering or positional information of the words within the document. For this type of analysis, we do need a particular data structure that's called a document term matrix. So in this type of matrix, each word is a row, each column is a document, and cells count the number of times the word appears in the document. So basically, it's a matrix consisting of the vectors that we talked about with the bag of words approach. Once again, we can see the topic modeling workflow in Tidytext. Rather than spend time talking through this, we are going to implement it in R. Okay. So we are back with our Taylor Swift example. Thankfully, Tidytext does have a very convenient function that converts our initial data frame into the DTM format that we need. And so that's this set of code here that I just ran. And so if we now just take a look at the DTM, it gives us some high-level numbers on the document term matrix. So here we can see that the sparsity is 99%. So 99% of the cells in the DTM are empty. And then, yeah, we can see that the weighting of the matrix is just term frequency. So it's going to be those counts that we talked about. If we want to take a look at what the terms are, we can use the terms function. And this tells us the first few terms in the matrix. And then in order to run a topic model, we're going to use the package topic models, aptly named. And one of the key decision the researcher has to make in topic modeling is the number of topics that are going to be identified. This, I'm sure Scott can provide more thoughts about this after, but from what I saw, it can be a bit arbitrary, but also the choice of topics can really affect the results. So it's important to try to have some theoretical reasoning for the number of topics that you select, but often it might not be there. And that is one of the main shortcomings of topic modeling. So I am arbitrarily choosing here to have 10 different topics that the model will identify. So I'm going to run this code on the document term matrix for Taylor Swift lyrics. And then we can actually look at the top terms for each topic it identified. So we can see we have a set of 10 different topics here. I don't really have any key insights on what these different topics could mean, but if you thought they did have different meaning that could be interpreted, then maybe it could provide us some insight into the Taylor Swift corpus. But I think we're seeing quite a bit of noise in the data with 8th, 5th, and Australia. So I think, as I mentioned, there are some speeches, maybe some people's names included where they shouldn't be. So I think what this is telling me is I need to go back and clean my data a little bit better. So yeah, that is the end of the R code that I have here. So I'm going to jump back into the slides. We can wrap up with the last few things here. Okay, so there are a variety of extensions of topic modeling. Shout out to ChatGPT for making this really nice table, summarizing all of them for me. Feel free to kind of go back and read this. I'm not going to spend too much time talking through it. But as you'll notice, the vectorization method here is still that bag of words approach. If my understanding is, it seems like if you want to use other types of vectorizations, you will have to use something other than a topic model, but that might be incorrect. Scott, correct me if that's wrong. Anyway, so basically, if we do want to use classification, we can also, if we want to complete more complex classification tasks, we can use supervised machine learning. This involves creating a training data set, training a model, validating the model, and applying the model to new data. And when you choose a model, you will also choose the type of vectorization. It's good to try multiple types of vectorization. So for example, if you were using an SVM model, you could try both the bag of words and the word-to-vec vectorizations. All right, and so then lastly, just wanted to take not too much time here to talk about other current research. I don't know if Justin was able to make it today, but this was one research article he flagged about how machine learning has been used to qualitatively code data with a hybrid iterative approach. And so what they found is that actually by incorporating machine learning and human coding of data, they were able to get the highest reliability of coding. And also it rescued some data points that human coders missed. And then there are a couple other articles by Laura K. Nelson talking about kind of the future of coding, computer-assisted text analysis methods, and then also computational grounded theory that are definitely valuable if you are looking to pursue this and also figure out how to incorporate some sociological theory into these methods. So yeah, that's all I have today. Look forward to having a bit of a discussion about it in the time that we have left.
Let's give a hand to Jenna.
Yes, Jacob.
Okay, so I have a quick thing about the topic models and then choose. There's a lot of choice involved in topic modeling, is what I've learned from reading about it over the past year and helping Howard out with the project. And in terms of like deciding the correct number of topics in a model, there's all these statistical measures that have been created to try and like figure out the optimal topic number that you want to sorry, sickness want to put into the model. But when people like have used these like statistical measures to try and optimize their topic models, the topics that they create are often like incoherent and like not super readable by people. And so I tend to like side with like the social scientists here who have like found like just use qualitative measures, because like what you're trying to get from a topic model is like coherence, ideally, or most people are trying to get coherence. And then so there's various qualitative like metrics that people have used to optimize topic models, involving like readability. Understanding. Maybe Scott disagrees with some of that, but at least my reading of the topic model literature is that the statistical measures not as useful, at least for what social scientists are trying to do, and the various qualitative measures and methods are better for determining optimal topic model like choices. Hopefully that made sense. Sorry, sickness is fogging my brain up a little bit.
Yeah, I mean, I tend to agree. I think, it's kind of an interesting history of topic modeling, where like the very first works were essentially trying to figure out how you best summarize all the kind of latent themes in a data. And so these kinds of original ideas were thinking like there's a true number of latent topics that are uniquely identified by the combinations of words that appear. And so the least biased solution is the one that best represents the data according to whatever efficiency predicted trade-off you have. So very statistical reasoning. But then, like, most of the people who actually wanted to use a topic model, they weren't really concerned with debiasing the data as much as interpreting it. And it turned out a lot of the patterns that were being detected with the least biased solution according to statistical principles turned out to like have a lot of incoherent categories, sometimes multiple categories that were talking about the same thing substantively. And so the interpretation that people want doesn't necessarily align with kind of the best fit solution. And that's actually totally consistent with like a shift you see in how regression has been applied from like the 1980s to today, where the 1980s it was like model fit, uber alles, and today it's more like get a good estimate. So, I mean, I think the practice and the what you're really trying to get out of topic model kind of depends on how much you're really concerned with interpretation versus things like topic similarity. So, like, I think for qualitative purposes, many people are using topic models simply to streamline the interpretive process, get a sense of what the themes are in the data. And at that point, really human interpretation is the most important thing, and topic modeling is just a tool to make it more efficient. There's other applications like in the social studies of science where people use topic models to try to figure out, how do fields emerge from different disciplines, how do subdisciplines emerge, and what types of topics are people working on together. In those cases, actually, you're trying to scale to big data. You have a lot of nuance and things. You can make a bit of a stronger argument to getting kind of an ideal solution because there is, in some theoretical sense, a fixed set of topics that people are trying to detect and quantify. And so I think there is kind of like a trade-off between what the research goal really is. Are you trying to create like a measure that you can reliably kind of compare across corpuses and across time? Or are you trying to facilitate interpretation? So I think there's kind of like, depending what you're trying to get out of the topic model with the research purposes, you prioritize one or the other. That's my take at least.
Yeah, Will.
Yeah, to follow up on the topic model stuff, there's also a massive amount of arbitrariness underneath the hood of topic models and how they do their sampling and from the underlying distribution. And when you get into the weeds on them, the arbitrariness has some problems for doing actual analysis, but they're also really good for exploratory work. If you have a big corpus that you're interested in, topic models are a great first step for just looking and seeing what's there, trying to get a sense of something. So not necessarily as the final step of analysis or even something that you would include in the methods, but just as a way to go, so I got 10,000 documents. What do I do with this now? And topic models are a nice way to quickly take a look at that by changing the underlying distribution sampling or changing the number of topics, seeing what pops up, and just kind of looking at what's there.
Sorry for the background noise. I have a quick question. So first of all, thank you, Jenna, for the presentation. It's like really informative and really helpful. I was wondering if there's a way where anyone has done work projects like combining these two methods that you introduced, like the sentiment analysis and topic modeling. Because I agree with like Will and Scott, what they're saying, like topic modeling is great for exploratory works, right, to uncover like main themes, right? But if I want to know more about like what's the kind of the attitude or what's the sentiment or tone around each theme, is there a way to combine these two methods that you covered today?
I don't have the answer to that, so I'm going to defer to Scott and Will if you have
Yes.
thoughts.
Yes, you can. So if you want to combine topic modeling and sentiment analysis, for example, if you have a corpus with like 5 different latent topics, then what you can do is just assign each document to a distinct topic and then conduct a secondary analysis within topic, which is just doing the standard dictionary-based approach to sentiment analysis. And so if you're kind of thinking about, I don't know, we're in the Taylor Swift world. So maybe like if her topics about America are different from her topics about relationships. I mean, on one hand, you might expect she could be more positive or less positive about America, depending on the stage of her career and who's in office. She could also be more or less positive about relationships, depending on the stage of her career. I'm guessing probably not who's in office, but those things vary over time as well. Probably stage of the life course, right, which would be highly correlated. So point being that you can do this type of sentiment analysis where you're trying to, I think oftentimes the sentiment and the classifications or the themes in the data, they can be correlated, but they really are distinct dimensions. So there are some sentiments that analyses techniques that really in some sense are trying to detect topics. Like you could envision like something about love could be related to a particular topic like relationships. But for the most part, they are kind of distinct. And so you can do it separately. Yeah. I want to put Will on the spot, which is we had this slide earlier about advantages and disadvantages of sentiment analysis. And I happen to know Will just published a paper using sentiment analysis where he fortified a lexicon. So I would like, Will, if you feel so bold and don't mind me calling you out right now, if you could like kind of reflect on some of your experiences and what you had to think through and kind of applying this approach and building a lexicon for the case data.
Yeah, definitely. I can do that. So one thing that I put into the chat, I'm in the same room as Jenna, so I didn't want to sort of talk while she had her mic open. So a few things that I worked through with doing the sentiment analysis. So the first is that if you're doing a sentiment analysis, you have to be really careful about what the text data represents, because typically we care about sentiment of things. It's kind of rare to just care about sentiment in general. There's something that it's connected to that's meaningful for a research question. So that can run into a problem when you have complicated text, where different sentiment words can be used connected to different targets, to different concepts. So using sentiment analysis in a newspaper article can be really complicated because you don't actually know what that sentiment is about necessarily. If the newspaper article is covering a movie review and they use the word bad, that doesn't necessarily mean that the movie is bad. It could be a bad guy in the movie. So the sentiment gets tricky. But because what we were using the sentiment analysis for were online reviews of drug sales, reviews tend to be really targeted in terms of their topic and really restricted in what people are talking about. Sometimes people go off topic and start talking about their vacations. People do weird stuff online. But pretty much entirely, people are super focused on how good were my products. So the data play a super important role in the utility of the sentiment analysis because you can be so sure or so unsure if it's bad data for it in terms of what the sentiment is actually targeting. And there are methods of like named actor recognition and ways of assigning that, but it starts to get to be really complicated and maybe not worth it. So one of the things that was really important was just the type of data and the target of the sentiment. Another thing that I had to deal with were out of lexicon words. Because this was a drug market, people used weird words and it was an international market. They sometimes use different languages. The primary language is English, but sometimes there's weirdness in there that you have to account for. There's also a lot of slang in these types of things that you have to account for. So one common thing that people did is they described their transaction experiences as being no bueno, which intuitively you're like, oh, not good. But that's just left out of the lexicon. So you have to decide like where does that fit and have some sort of logic of what number to assign because they use the AFIN lexicon. And the sort of logic was, I don't know, what words does this seem similar to? Spanish for good, assign it to whatever good is. And then incorporating the no part, dealing with those sort of negations is something you can do pretty simply in a sort of unigram approach because you can just tokenize bigrams. So you just take the word that's before it, and then there's a set of shifter words, and you can just multiply the sentiment of the good or bad word to whatever its inverse is, and that can provide a good sense of sort of shifted and negated sentiment in your corpus. Other things, it's really computationally not intensive, which is great. If you don't have a great computer, sentiment analysis doesn't care. It's really simple to do on pretty much anything. And that's a thing that you have to really keep in mind for a lot of these text analysis things is the amount of effort and time that'll go into whatever your product is, where sentiment analysis, really easy to get up off the ground. The topic modeling, really easy to get up off the ground. Training your own classifier, that's a lot of effort. And also really computationally intensive, but you can get a lot from it if you can actually do it. So that was another one of the big things that had to keep in mind for actually using the sentiment analysis is that going forward with it was as easy as loading it into R, tokenizing it, knowing how to interpret and make sense of the data, and then using the scores and figuring out how to actually use those in statistical modeling. That's just the stuff off the top of my head, but anything you had in mind other than that?
No, just whatever was on the top of your head.
Yeah.
I think one of the other neat things about sentiment analysis is kind of like the most old school NLP technique was just dictionary approaches in general. So like if you look at kind of the very early work on natural language processing from like the late 90s and early 2000s, it was really just people trying to create their own dictionaries for whatever they were trying to detect. And so like sentiment analysis is kind of like in some ways like one of the last vestiges from this era where the dictionaries have been so well expanded and established that people really know how they perform works, what doesn't, how to modify them. But it's really a broader range of tools that you can use if you really feel like making it. Do we have any final thoughts or questions before we wrap up? Young?
Yeah, my question is, I have not read into this for a while. My question is that, how does this text analysis develop in the large context of the large language model? Because as Will point out, this is in many ways, does not require that much computational power, partly because it's not as sophisticated as the large language model. So, and the AI tools now available to us creates and provides a much better context. If we need the context is right there. It's built right in the large language model. So I have not read into this. So my question is, hey, what's the connection between the two, and how can we leverage the newest tool available to us?
Yeah, it's a very big question. So, I mean, the large language models under the hood really rely on a similar data structure. Like they're essentially just tokenizing words and then figuring out relationships between them. Where it really departs is like, so a particular text analysis application that social scientists don't do as much of, but what large language models primarily do is word prediction. And so the idea is that based on some set of cues, they can kind of identify some corpus of words and then predict what the next most likely word to occur is. And so large language models are really essentially what they're trying to do is detect relationships between different word tokens that can allow them to predict very complex passages out of kind of sometimes vague prompts and the relationships between words that they already have. So the kind of one way to think about it is really as a hierarchy of classification. So the simplest classifiers that you can have for text data is just does a text exhibit a theme? A sentiment analysis is really a slightly more advanced classifier that just combines the outputs from classifications of individual words. Then you get to kind of the unsupervised and supervised classifiers that people typically work with, like topic models, which are relying on correlations between words, and then supervised classifiers, which are also doing correlations between words, but are doing it based on some training data or input data that you're telling it to learn. The large language models are kind of the cutting edge of what we think of as text classification these days. They're relying on neural networks, and which is just a type of deep learning. And basically, the gist of what they're doing to discover relationships is they are iterating between text inputs and outputs at multiple layers. So the idea behind a neural network is you have an input layer, you have a processing layer, you have an output layer. That's the simplest neural network. So a simple supervised learning algorithm, you have your input layer, which is training data, your processing layer, which is the algorithm actually learning it, and then your output, which is your text predictions. What a neural network is doing is extending those layers so that the output of a prior layer becomes the input to the next layer. And when you do this, you can actually write different gain and loss functions that allow the processing at each distinct layer to teach itself. And this is why neural networks can be really good at detecting like interactions, nonlinearities, and combinations of words that are really hard for other algorithms to learn because it allows for really arbitrary dependent structures because everything's updating on itself. So large language models are extremely complicated, very, very deep neural networks that have a lot of internal updating and processing. And this is also why it's really hard to figure out how they work because there's usually so many layers that are teaching themselves in unpredictable ways that essentially we have, thousands and thousands and thousands of layers, if not millions, all of which are updating one another. And so they don't even have fixed gain or loss functions. They're learning what is the best according to predictive performance. And so this is why, on one hand, LLMs work so great is because they can really detect complexities that the simple kind of classification algorithms struggle to detect. But it also means that they're also extremely hard for people to understand why they're doing what they're doing and why the hallucinations that they produce can be just so unpredictable and off the wall because they are picking up on really hard to detect signals that occur in the data that we often can't actually figure out where they come from because there's so much complex processing going on. And again, because of they have essentially like one way of thinking about an LLM is it's like you take a standard supervised classifier like a support vector machine, and it's something like a million of those just strung together, updating the loss functions at every iteration. And that's why they cost so much data and so much energy and computational power is just because of how much is actually going into. So anyways, this is a pretty long-winded response, but I mean, if we think about these kind of like hierarchies of classification where at the simplest level, we have an if-then statement, then we have in sentiment analysis, a combination of if-then statements, then supervised and unsupervised learning, we have statistical procedures to detect patterns. And then at the highest level of deep learning and LLMs, we're essentially chaining all of these processes together into something that's extremely complex, difficult to detect, but also very, very difficult to understand, but very, very good at extracting nonlinearities and complex relationships. I'll pause and let Will do this thing.
Yeah, I think that there's a couple big things about them. The first is that not being able to figure out why they do what they do has traditionally been a really big problem for them and has stopped a lot of people from actually publishing their work using those types of algorithms, because when they start to look internally inside the black box about why some documents are assigned to some category or something, they get really weird results and they just have no idea why the weights are what they are. And that has traditionally been a really big problem. I think the appetite for them, though, is growing a lot, and people are much more willing to ignore that black box problem than they have been in the past. So one project that I've heard of is just using ChatGPT to tell you what Schwartz values are in a type of text according to the guy who made up Schwartz values. And those are just like how much people like moral values of things. And it's just like the type of thing that people are working on now, telling the LLM, take on this persona and code these data according to this persona. And I think if you rewound 15 years, that person would be called absolutely deranged. But because of how popular and common LLMs have gotten, I think people are way more comfortable with just accepting, yeah, we have no idea how it works or why it works, and we don't know what the weights are doing, but it produces something cool and interpretable, so we like it. So I think that's another important part about what LLMs are and how people have started to actually interact with them.
I will just raise a word of caution to students who want to use LLMs for sociology research, which is there has been very strong resistance at pretty high levels from use of LLMs in sociology journals. So, for example, Laura K. Nelson, who Jenna cited earlier and is a very large figure in text analysis, has a very strong belief we should not ever use ChatGPT for research because it's not transparent and people don't know how it's working. I also have heard through the grapevine that the ASR editors, after they took over, had a bunch of papers that were pretty late stage in the review process with R&Rs using LLMs. And apparently they rejected them all because they didn't want any LLM research in the journal. So I do think it's something that I think there's a lot of excitement and opportunities around it, but be aware that this concern about transparency and reproducibility, it seems to be a contentious issue that has not fully come to kind of like public light yet, at least in sociology circles. Okay, we're about 10 minutes over, so unless there's any final comments